Russian and Soviet space history launch vehicles. R-7, four-stage version of R-7, Korolev, 300 metric ton gross liftoff mass, available from 1960 for robotic lunar and interplanetary flights. This would be the Molniya 8K78 booster. Removal of the fourth stage resulted in the Vostok 11A57 launch vehicle used for launch of later heavier Zenit and Vostok spacecraft. R-7L, Korolev. Developed in 1960 to 1962, a four-stage version of the R-7, utilizing R9 technology, with a 300 metric ton gross liftoff mass and high specific impulse engines in the last stage. Payload 10 metric tons to low Earth orbit and 3 metric tons to escape. Draft project to be completed in 1961, this booster, later called the Molniya 8K78L, was never developed. UR-500, Chelomey, develop a 600 metric ton gross liftoff mass rocket using new chemical propellants for sending spacecraft to nearby planets. Draft project to be completed in 1962. This would become the UR-500 Proton booster. NI, Korolev, to be developed in 1960-1962. Booster with 40 to 50 metric tons payload to low Earth orbit and 10 to 20 metric tons to Mars. Draft project to be completed by second quarter 1961. N2, Korolev, to be completed in 1963-1967. Booster of 60 to 80 metric ton payload to low Earth orbit and 20 to 40 metric tons to Mars. Draft project to be completed in 1962. Manned spacecraft. Vostok recoverable spacecraft, Korolev. Photo and electronic reconnaissance versions to be developed in 1960 to 1962. These would be the Zenit 2 reconnaissance satellites. They would end up flying after, not before, the Vostok manned flights. Manned version to be developed in 1961 to 1963. These flew on schedule. Scientific research version to be developed in 1960 to 1962. These were designed but never flown. Maneuverable rendezvous and docking version to be developed in 1961 to 1963. This was the Vostok Z, never flown, replaced by Soyuz. KS, Korolev, heavy manned spacecraft, 2-3 crew, to demonstrate rendezvous, docking, and controlled flight. To be developed in 1961 to 1963. This would become Soyuz A. KL, Korolev, manned spacecraft for lunar flyby. To be developed in 1961 to 1964, this would go through May design iterations and political intrigues, ranging from the L-1 1960, L-1 1962 to the Soyuz A. However, Chelomey would be assigned the project, LK-1, only to have Korolev get it back in 1965 and finally reach flight status as the Soyuz 7K-L1. Korolev also studied lunar automatic crawlers, L2 1963, manned lunar landers, L3 1963, manned lunar orbiters, L4 1963, and manned lunar crawlers, L5 1963. The lunar L3 lander project was authorized in 1964, and the L2 emerged as the Luna Yi-8 Lunokhod. KMV, Korolev, interplanetary manned spacecraft for 2-3 crew, flyby of Mars and Venus. To be developed in 1962 to 1965, this was the TMK-1. This design would evolve into full-blown Mars landing expeditions during the course of the 1960s. TMKE, Maver, KK, scientific and planetary spacecraft. M, Korolev, launch of Mars 1M robot probes in September, October 1960, and 2MV probes in 1962. These Mars flights were attempted on this schedule. These used the three-stage Luna 8K72 version of the R-7 authorized in 1959. V, Korolev, launch of Venera 1VA probes in January 1961 and 2MV probes in 1962. These Venus flights were attempted on this schedule. These used the three-stage Luna 8K72 rocket. E on Korolev, launched to the moon as per the decree of 10 December 1959 of Luna E1, Luna E1A impactor probes in 1960 to 1961, and Luna E3 orbiters in 1961. These used the three-stage Luna 8K72 rocket. They were followed by heavier Luna E6 lunar soft landers launched by the Molniya 8K78 booster. Chelomey. Development of unpiloted cosmoplans for flight to Mars and Venus, with return to Earth and landing at conventional airfields. These would use new exotic chemical systems, low-thrust nuclear engines, nuclear plasma, ion, atomic hydrogen. Subvariants with a total mass of 10 to 12 metric tons and 25 metric tons would be developed in 1965-1966. Draft project to be completed in 1962. Electron, Korolev, High Apogee Radiation Belt Research, Electron A and Electron B satellites, developed according to decree of 10 December 1959, to be launched in 1960 to 1961. These flew late to schedule. Military spacecraft. USA, Chelomey, Naval Reconnaissance Satellite using P-6 nuclear reactor. Derivative of the Cosmoplan to be developed in 1962 to 1964. These flew late to schedule. R. Chelomey, manned Raketoplan spacecraft for orbital maneuvering, flight, and recovery at conventional airfields. Total mass to be 10 to 12 metric tons, total gliding range during re-entry to 500 to 3,000 km. Unpiloted version to be developed in 1960 to 1961, followed by piloted version in 1963 to 1965. Satellite interceptor operational version to be tested in 1962 to 1964. Only suborbital subscale tests were conducted on this program before it would be canceled. One variant became the LK-1 manned circumlunar craft, canceled in turn before it flew. Meteorological satellites, Korolev. Meteor R-7 launched satellites to be developed in 1961 to 1963. These would fly, but behind schedule, to be followed by heavy rocket satellites in 1963 to 1964. Designer not decided. Communications satellites, Korolev, R-7 launched satellites to be developed in 1961 to 1963. These would fly behind schedule as the Molniya-1 series, to be followed by heavy rocket satellites in 1962 to 1964. Designer not decided. DS. Small satellites, launchers, Yangel, to be developed in 1961 to 1965 together with the Cosmos 2 and Cosmos 3 launch vehicles derived from the R-12 and R-14 ballistic missiles. This program flew on schedule. Early flight tests included 1MS, 2MS prototypes from another design bureau. OS, Korolev, space stations. The Ministry of Defense was to decide by the fourth quarter of 1960 whether it can utilize military stations with multiple independent rocket warheads. This design was iterated through many versions: TKS Heavy Space Station, OP, OS-1, 1965, OS-1, 1969, into the MKBS space station during the course of the 1960s. The cancellation of the N-1 in 1974 would finally kill further work on large space stations in Russia until later versions of Mir-2 in the mid-1980s. Its anti-satellites, the Ministry of Defense was to decide by July 1960 whether to develop an R-7 launch system for annihilation of enemy reconnaissance satellites. This project was conducted but given to Chelomey for launch on the UR-200, eventually flew in the late 1960s as the ISA launched by Yangel Cyclone 2 rockets. Military communications satellites. The Ministry of Defense was to decide by the fourth quarter of 1960 whether to proceed with development of military communications satellites. This was done. The Strela 1M and Strela 2 series. The final government decree 715-296 of 23 June 1960 on the production of various launch vehicles, satellites, spacecraft for the military space forces in 1960-1967 authorized draft project work to begin on this massive agenda. Meanwhile, the projects authorized in the 1950s were underway, maintaining the Soviet lead in the space race. In January 1960, Star City, the Cosmonaut Training Center, was founded by the Soviet Air Force, and Kamenin was made the head. The first cosmonaut candidates arrived in March 1960. Following unmanned flight tests of Vostok 1KP, Vostok 1K, and Vostok 3KA configurations, Yuri Gagarin made the first manned spaceflight on 12 April 1961. 5 further manned Vostok flights maintained the Soviet lead in the space race. In order to keep up with the Americans, Korolev developed and flew a multi-crew version of Vostok, the Voskod 3KV, and a Vostok with an airlock to accomplish the first spacewalk, the Voskod 3KD. Further Vostok and Voskod flights, such as the Voskod 3KV tether experiment, were planned but canceled in order to concentrate on the more capable Soyuz spacecraft. In parallel with Vostok, the more sophisticated Zenit 2 and Zenit 4 photo-reconnaissance variants of the spacecraft reached service. Zenit 2 flights began in December 1961. 13 were flown in 2 years. The system was accepted into the military service in 1964. Zenit 4, the high-resolution version, followed in 1965. First-generation Soviet space systems. The Soviet military realized that having the chief designers define space systems was a bottom-up approach that did not address the country's real needs. They were faced with an immense American buildup of ballistic missiles which they could not hope to match if resources were squandered on grandiose space projects. Therefore, measures were taken to obtain control of the situation. A July 1960 declaration listed the military systems to be developed in 1966 to 1970. Military research programs of 1962 to 1964, codenamed Szczyt space systems, Osnova space equipment, and Edini Kik ground systems defined the first generation of Soviet operational space systems, deployed in 1966-1975. First-generation systems were often developed by Korolev, then spun off to other design bureaus for production. At the beginning of the 1960s, an unwieldy total of 30 space systems were in development. In the early 1960s, Russian strategic nuclear forces on land, sea, and air were already in place. The military wished to integrate military space forces with these in a systematic manner as soon as possible. These requirements resulted in definition of an SKV, Space Military System. The SKV would exploit the global range of orbital systems, determine the precise location of mobile and fixed targets for strike by strategic forces, precisely hit such targets, and quickly and securely transmit targeting information. A hallmark of the early 1960s was a militarization of space under the shadow of Kennedy's policy of massive retaliation. Both the US and USSR deployed unmanned and developed manned systems to identify, track, and destroy the enemy's satellites. ABM systems could also be used to hit satellites in orbits up to 200 km. This process of militarization of space was only averted in the Soviet view by actions taken by Nixon in the 1970s, the SALT I Treaty, the ABM Treaty, and secret understandings to stop development of anti-satellite systems. The period 1966-1970 featured the first practical use of space systems of the first generation. First-generation satellites were very unreliable. One problem was unrealistic specifications, another a lack of proven space-worthy components. The first solution was redundant systems, and these were tried on an experimental basis in the Meteor, Strela, and Cyclone satellites. Flight demonstrations proved use of better construction methods would allow guaranteed satellite lifetimes of 2 to 3 years. Meanwhile, the operational situation reached a crisis point. The USA had faced the same problem and developed a strong, reliable component basis for spacecraft. This had increased individual American satellite lifetimes to 3 to 5 years and system operational lives to 5 to 7 years through use of on-orbit reserve spacecraft. But in the Soviet Union, due to the urgency to deploy, there was no time to develop such a technical basis for first-generation systems. Only in the 1970s were reliability problems solved through use of qualified standard components, standard means of documentation, and quality assurance. While the reliability of first-generation systems was poor, they still met the needs of the rocket forces and general staff. Quick reaction, 10 to 12-day launch times were achieved, and the new systems allowed precise targeting of long-range rockets and naval forces. The Korund space communications system provided reliable command and control of the strategic forces. Military space operations began in 1961 with the Provisional Rocket Engineering Auxiliary, VANR S-61. This initially developed military operational plans for launch sites and command and control activities, including regularly scheduled maintenance operations. This first phase, which prepared the military to execute space operations and conduct trials of systems, was completed by 1965. The first military space operations plans were prepared for the Zenit Reconnaissance Satellite System in 1964 to 1965 and subsequently used by the General Staff in the operation of that system. Target identification and location, photo reconnaissance, cartography. While Korolev had designed the first such satellite, the Zenit 2 detailed design of the Zenit 4 high-resolution model and production of all follow-on spacecraft was handled by Kozlov. In mid-1967, plans were approved for further development of these models through 1975, taking into account work then underway. The results were the improved Zenit 2M and Zenit 4M satellites, taken into military service in 1970 and 1971. Yantar follow-on reconnaissance satellite. Originally, Yangel was to handle Yantar, but his design bureau was too busy building higher-priority ICBMs for the RSVN rocket forces. So Kozlov took up the project in 1969. Yantar 1KF and Yantar 2K test construction work began in 1970, but the new series of satellites would be completed only as second and third generation systems. Manned photo reconnaissance draft projects for two such designs, Kozlov's Soyuz R and Chelomey's Almaz Apas, were authorized in 1964. Soyuz R was canceled when it became too heavy for the planned launch vehicle. The Almaz, a dedicated platform for manned high-resolution multispectral study of specific targets, continued. The flight trials were intended to prove the effectiveness of manned orbital reconnaissance operations. The program was to take place in two phases. Phase 1 would man the space station using crews shuttled by Korolev's Soyuz 7KTA-9 spacecraft. Phase 2 would be the operational system, serviced by Chelomey's much larger TKS manned resupply spacecraft. The program was delayed for 2 years when Almaz hulls were diverted for the Salyut 1 DOS crash programmer to launch a space station before the American Skylab. Finally, the first Almaz was launched in April 1973. It depressurized and was abandoned before the crew could be launched. Salyut 3 in 1974 and Salyut 5 in 1975 to 1976 were successfully manned. But the results of the flights showed that manned reconnaissance was not worth the expense. There was minimal time to operate the equipment after the crew took the necessary time for maintenance of station housekeeping and environmental control systems. ELINT, Electronic and Signals Intelligence. An initial capability was provided by the Zenit 2, which carried the Kust ELINT apparatus. From 1965 to 1967, two dedicated ELINT systems were tested, the Selena and the Navy's US. Both reached service, since the Ministry of Defense could not force a single system on the military services. Selena was developed by Yuzhnoye and consisted of two satellites, Selena-O for general observations and Selena-D for detailed observations. ELINT systems for Selena were first tested under the Cosmos designation in 1962 to 1965. The first Selena-O was launched in 1970. The Selena-D took a long time to enter service due to delays in payload development and weight growth. The Navy's U.S. radio intelligence satellites were built in USP, passive detection, and USA, nuclear-powered active radar variants. Development was begun in 1960. They were descended from Chelomey's Cosmoplan modular spacecraft design and were part of an integrated naval warfighting system, feeding locations of enemy naval forces to Chelomey-built ship-launched cruise missiles. Both satellites were designed for launch by Chelomey's UR-200 rocket. On October 13, 1964, Khrushchev, Chelomey's patron, was ousted from power. The new leadership decided to assign the U.S. project to Savin, with Chelomey in the subcontractor role to be launched by Yuzhnoye's Tsiklon 2 rocket. Delays resulted in the U.S. being implemented as a second-generation system in the 1970s. Television reconnaissance. Chelomey began project work in 1963 on the Space Television Reconnaissance System, TGR. Savin had developed the original concept, but it was found that the technology did not yet exist for even a draft project to be completed. The concept would not enter operation until the Yantar series in the 1980s. Navigation. Tsiklon, the first Soviet navigation satellite system, was designed by Reshetnev. Experimental flights began in 1967 in order to develop a system meeting the required tactical and operational characteristics. The Tsiklon B operational system provided not only navigation information, but also store-dump radio communications for Soviet naval forces. The system was accepted into military service in 1976. Meteorology. The Meteor satellites were developed as per a decree of 30 October 1960. Work began in 1961 at Yuzhnoye. In 1962, it was transferred to VNEM. Final development was completed in 1964. The system went into operation in 1969. Geodesy Reshetnev's Sfera geodetic spacecraft allowed measurement of geodetic points, leading to improved accuracy of long-range weapons. Flight tests were from 1968 to 1972, and operational flights were from 1973 to 1980. The Cosmos 3M launcher was used. Strategic and tactical communications. Strategic communications. The strategic communications requirement was met by the Molniya-1 developed by Korolev. This used an elliptical 12-hour orbit that could be reached by existing launch vehicles and was better suited than geosynchronous orbit for communication with polar areas of the Soviet Union. The experimental version of the spacecraft proved so successful that it was put into service. Reshetnev was responsible for production and follow-on models. The entire system, designated Korund using existing Gorizont military tropospheric communication ground stations, went into partial operation in 1968. The Molniya II model was developed to accommodate the Orbita television system and was operational by 1972. The Rushi Command and Control System communication stations for the rocket forces, Air Force, and Navy were completely in place by 1975. Korund allowed strategic communications and telephony with military units in Siberia and the Far East. The system finally included 8 spacecraft, replaced at increasing intervals as reliability improved over the 20-year life of the system. Tactical communications, Reshetnev's Strela, medium Earth orbit store dump, survivable communication system was developed experimentally in the 1960s, with flight tests from 1964 to 1965. Production system flight tests began in 1970. In 1973 and 1974, the Strela 1M and Strela 2M systems were accepted by the military. This system proved the basic concepts used in the Iridium and Globalstar commercial satellite constellations decades later. To be continued.